recorded for chapter 15. So chapter 15 is all about our special senses. So special senses are any sense that we have that's located solely in the head and neck, right? It includes sight, smell, taste, hearing, balance, and equilibrium. So those are the 5 main special senses. Take a look at this, right? This is the cochlea. The cochlea looks like a little shell, right? You can imagine a snail shell. And we're gonna see the cochlea itself is gonna be incredibly important in how it functions. Now I can imagine, we're not gonna go into details about hearing until next week, Monday. Right? Now, let's discuss taste and smell today. If we get taste and smell today, we're in great shape for next week. Taste, or let me rephrase that, smell, right? In terms of smell, we have 7 primary odors. I think we have more now since this book was published, right? Average person can recognize 4,000 different odors. And those odors are perceived by olfactory neurons that come through the olfactory bulb and then embeds itself on our superior part of our nose. The funny thing is this, right? The funny thing is we have distinct cells called olfactory hair cells. Those olfactory hair cells have what looks like little hairs right here. And those hairs up there will allow us then to bind with molecules of smell, odorants, right? But in order to bind to it, we need a thin layer of mucus. So we do need a little bit of mucus. The mucus in our nose not just traps dust, but it also helps trap odorants. Without a thin layer of mucus, you take a deep breath in, all the odorant molecules goes deep into your nose right away, and then goes into your throat, right? You don't give time for the odorant molecules to bind with our olfactory hair cells. If you don't give it time to bind to it, you don't trigger these cells to activate and to activate our olfactory cranial nerve, right? So you need a thin layer of mucus. That thin layer of mucus then traps the odorant molecule as you take a deep breath in with your nose. Now, if it's too thick, the mucus now, instead of being just this little thin layer, is now big and thick, like when we get sick and we get a stuffy nose. What happens when the mucus layer enlarges? You can trap the molecules better, but the molecules are trapped way down here now instead of up here. Because they're trapped because the layer of mucus is so large that you're trapping it way away from the hair cells. The odorant molecules can't make contact with the hair cells. It's too far away. And that's why when you're sick, that's why when you are having a stuffy nose, that's why you can't smell anything. That thick layer of mucus traps the odorant molecules. Perfect, but it traps it too far away to make contact with the hair cells. So even though we trap the molecules, we can't have the molecules combine with the receptor, right? We don't smell it then. Right? Olfactory neurons are replaced by basal cells every 2 months. One of the rare times when we do see a reformation of the hair cells and the neurons here. Now, important thing to note, notice that a lot of this isn't highlighted. I do want to mention that when we looked at the cribriform plate, do you remember that in the first lab practical? The cribriform plate was part of our ethmoid bone, right? It was found on the lateral sides. Basically, medially was a cribriform, was a crista galli moving up, and then you have 2 combinations of holes, right? Those holes are these right here. Those holes found in the cribriform plate allows your olfactory neurons, right? Allows them to go from your brain into your nose. Perfect. Allowing us to connect our cranial nerve number 1 to our receptors for smell. Now, what else do I want you to know? This part. Information for smell goes to the olfactory cortex found in the frontal lobe. This is the part that I want you to highlight and underline. If I highlight and underline it, you know it's going to be on the test somehow. So do not get this wrong. It is the only major sensation that does not go through the thalamus. Period. Right? When you see questions like that and you see statements like that, right away, it should be a bling, 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 right? It should be like a sign that it's going to be on the test somehow, right? Only major sense that does not go through the thalamus. If you guys get that one wrong, I will take out 2 points, right? So get that one right, because I highlighted, underlined it, and put it in italics. So it's the only major sense, and I repeated it a third time. Only major sense that does not go through the thalamus. Whoops. Now what else do I want you to know? 3 regions of the frontal lobe affects conscious perception of smell, and then later on interacts with the limbic system. The limbic system is our pleasure pain center, right? Now, there are 3 regions. The lateral olfactory area, right here, right? Actually, right here. The lateral olfactory area allows us to have conscious perception of smell. Medial allows us a visual and emotional reaction to odor. The intermediate allows for adaptation of smell. Now, we talked about adaptation on Monday. Keep in mind, adaptation is this. When you put cologne on, when you put, right, perfume on in the morning, when you put it on, you smell it. It smells great, right? But what happens 20 minutes later? Do you keep smelling it? No, right? What happens then is you stop smelling it. The same stimuli no longer causes an action potential. And because of that, you no longer have that sensation of smell, right? You go to work, you go to school, and the person sitting next to you then, right, smells your perfume and cologne. And they always have to make a small remark like, what did you do, bathe in it? The funny thing is this, after a few minutes sitting next to you, they also adapt. And because they also adapt, they also stop smelling it. Crazy, right? But that is what happens with adaptation. It allows you to adapt and no longer trigger action potentials with the same stimulus. Now, if you put and reapply cologne, that's a stronger stimuli. You might smell it again. But after a few minutes, you also will adapt to that new smell. So this intermediate area allows for adaptation. It's highlighted. I want you to underline it as well. Lateral, conscious perception of smell. Medial, visceral and emotional reaction to smell. Right? Now, that's it for smell. The weird thing about a lot of this is that we know only the basics. We really don't know what really happens in the brain matter that causes us to have this conscious perception of smell. The next one I'll go through is taste, right? Taste is a combination of taste buds as well as, right, other papilla that allows us to have texture, right? So in terms of taste, when you get out of our class, I want you to look in a mirror. I want you to stick your tongue out in the mirror. And you'll notice if you look really closely that there are bumps on your tongue. The bumps are the papilla that we're talking about here. Those bumps, some of them contain taste buds, some don't. So there's four main papillae, right? And those papillae are the little bumpy things that we see. Some of the bumps are larger than other ones. So if you stick your tongue completely out, if you look at the back of your tongue, you'll notice that it contains huge papilla compared to the front. Now, some of you guys have eaten pineapples, right? If you've ever eaten a pineapple and you're like me, I love pineapple, so I overeat pineapple. The next day, your tongue just feels like it's raw, right? It feels like somebody just scraped up all your, the epithelium in your tongue. It just feels it's painful, right? Well, what happens is we do have pain receptors in the tongue, and with the eating of pineapples. There are little tiny fibers that does cause some of these papillae to be injured, and it causes inflammation as a result of it. So we have 4 main papillae: filiform, vallate, fungiform, and foliate. Now the weird thing is, the most common one, the filiform, has no taste buds connected to it. So you're going to ask me, why do we have these papillae, these things that go up and down our tongue? Why is the most common one not having taste buds? Is because the most common one isn't for taste sensations at all. It's there for texture, right? You guys have probably eaten something, and when it's warm, the texture is different than when it's cold. Soup is one of those, right? When you eat soup, you will notice that when it's cold, there's a different texture and flavor to it. So why do we think it's different? Warm versus hot versus cold is because of these guys, the filiform, right? Because of the change in temperature, there's a change in texture that's felt by the filiform papillae. So even though it's got no taste buds, right, that change in texture does influence how we think, right, the soup tastes. The vallate one are the largest. Those are the huge ones found at the base of our tongue, right? They do contain taste buds. They're found in V-shaped border between anterior and posterior part of the tongue. Fungiform ones also have taste buds scattered irregularly throughout the superior surface of the tongue. These are the ones that look like small red dots. Foliate, leaf shape, found on the side of the tongue. They contain the most sensitive taste buds. So what do I want you to know? Which ones don't? And the ones that do, which ones are the most sensitive? The foliate ones are most sensitive, and they decrease in number with age. Now, how many of us have had a beer when you were like 12, 13 years old, right? I did that to my son, right? I didn't want him to drink prematurely, so when he was 12 or 13 years old, I forced him to have a drink of beer with me. He understands how bad it tastes, right? What happened? When he tasted it, and I took the most bitter beer too, right? Like dark, right? Dark, Guinness, warm, the way they should have it. Oh, it was terrible, the face he gave me. So after he had that taste, their taste buds were so sensitive to that bitterness that immediately, right, he almost puked it out. Perfect. I know he's not gonna drink beer for a while then. So what happens is, with time though, these taste buds start to decrease in number. So when you turn 20, 21, 24, 25, right, you don't have that same foliate. You don't have the same sensitivity to that bitterness. So then the beer that tastes so nasty before, well, you're no longer so sensitive to it. And now it tastes a little better, right? That's true for like even food. How many of you guys ever had like certain foods that you know tasted gross to you when you were a kid, and then you tried it again as an adult, and it's not quite as bad, right? Why? Because we lose that sensitivity with age. Now, taste buds are a combination of our support cells and our main taste or gustatory cells. All right, these taste cells have sensory neurons connected to it. So here's what the papilla looks like, right here, right? And then when we look, this is what a taste bud looks like within the papillae, right? Right, the taste bud contains taste hair cells that activate for sweet, salty, umami, right? All of those. And when you activate these taste cells, they release a neurotransmitter that then activates either your facial nerve or your glossopharyngeal. Remember, these neurons that are attached to our taste buds, those neurons are either connected to the facial nerve, allowing us to have taste sensations on the anterior 2/3 of our tongue, or if it's on the posterior third, all of these neurons are part of the glossopharyngeal. The weird thing is this, even our throat and epiglottis has taste buds. So we notice this. How many of you guys have eaten like a saltine? And then when you first eat saltine, it is really salty. And then as the enzymes start to work on the starches, right before you swallow it down, you taste a hint of sweetness, right? Why do you taste that hint of sweetness, even though it's no longer at your tongue? Is because the back of your throat, as well as your, right, epiglottis, they have taste buds connected to it. All right, so they have taste buds connected to your epiglottis and your throat. That allows us to have taste sensations, even as we swallow, which is weird, right? The weird thing, again, is that we actually, for your throat and the epiglottis, we have a different cranial nerve that carries that information. So your tongue, glossopharyngeal, posterior third, facial, anterior third, the throat, the pharynx, and your epiglottis, taste receptors and taste buds, right, will be carried in by the vagus nerve, which I have later on, right? Now, I would rather you guys also figure this one out, right, in terms of the 5 main tastes: sour, salty, bitter, sweet, and then the last one, umami. Now we know there's probably a few more, but these are our major taste sensations. You can't break it down any more than this. Now, example, how do I describe to you, or how do you describe to somebody else what sour tastes like without using the word sour, right? Try to do that one time. Try to describe what sour, what salty, what sweet tastes like without giving an example and without using the word. So sour, how do you describe sour without using sour? Hard, right? So this is our main, one of our primary tastes. It tastes sour like a lemon. Well, what if we don't know what a lemon tastes like? How do you describe it then? Really hard. This is why it's one of our primary taste sensation. Same thing with salty, right? What does salty taste like without using the word salt, right? Hard. So saltiness, because our body needs it, shares the lowest sensitivity along with sweetness, and along with sweetness is the easiest of the tastes to adapt. Let me ask you, and we kind of asked that before on Monday. When you have a potato chip, isn't that first potato chip so incredibly salty? It is. And then you have another potato chip, and then another, and then another. Eventually, right, you adapt so quickly to it, by the time you're done with the bag, you're licking your fingers, right? That's the reason why it's simple. Our body wants to adapt quickly and wants to ingest quickly things that it needs. It needs salt, right? Our body cannot make sodium chloride. It cannot make potassium chloride. So you can understand, as we were evolving, right? As we were, right, starting to become a civilization. And even now, certain parts of the world, it's hard to get salt. Salt is incredibly important, right? For action potentials, for water balance. So we need salt. So it makes sense that when we do eat something that is high in salt, what happens? You adapt quickly, so then you can eat more of it, right? Not only does it adapt quickly, it's got low sensitivity, meaning that it takes a lot of that salt for you actually to taste the saltiness. By the time you've eaten it and taste the saltiness, you've ingested a lot of it because it takes so much to activate that taste sensation. Perfect. Now, the good news is we get a lot of it in our diet. The bad news is we get a lot of it in our diet now, right? So we haven't adapted as we have increased amount of salt in our diet. Bitter, highest sensitivity. Why? Because most things that are bitter are slightly toxic or very toxic. The last thing we want to do with bitter is require a large amount of that before we taste the bitterness. If it takes a large amount, you're going to swallow it and then ingest all that toxin and then feel the bitterness. Doesn't make sense. You'd be dead by now. All right. So with bitterness and toxins, we want very little of the toxin to then activate the sensation of bitter. That's why we have, right, highest sensitivity. So then all it takes is a little droplet of it, and you taste that bitterness, and immediately you stop eating it because it's so bitter. Sweetness, very similar to saltiness. Low sensitivity, high adaptability, right? Now, that high adaptability allows us to ingest more of it. Again, I love Leon's, right? Even more than any other type of ice cream. Much better than Cops. So at Leon's, you get the tin roof sundae. As you have the first bite and it's super sweet. What happens? Well, you start to adapt real quick. As you start to adapt real quick, right, it takes more and more of that sweetness to actually trigger that initial response. So you eat it, you start to adapt, and by the time you're done, you're licking the, right, your spoon, trying to figure out if you should get another one, right? Why? Is because sweetness usually means carbohydrates. These are things that our body needs. The carbohydrate is broken down to glucose, then we can make glycogen out of it, and we can make fat out of it. Keep in mind, it's only very recently that we get carbohydrates in all of our, right, nutrition almost on a whim. We know when our next meal is coming. About 100 years ago, you might not eat for a couple days and then have a big meal, and then not eat for a couple more days and then have a big meal, right? So what happens? When you eat, you want to overeat so then you can store, right? When you eat something salty, you want to overeat so you can store it for later. Umami, scattered sensitivity caused by amino acids, right? Now, by the way, I put NutraSweet here, right? NutraSweet, like aspartame, it has 0 calories or sometimes 1 calorie for a reason, right? NutraSweet is a modified amino acid. Amino acids really don't have any calorie. It's not a sugar. Now, the last type of taste is umami. Keep in mind with umami and glutamate, right? It is activated by amino acids / mushrooms. Try to describe what steak or chicken tastes like without using the word chicken, right? Usually we use everything and refer to chicken. What does turkey taste like? Well, it kind of tastes like chicken, right? What does frog legs taste like? Kind of like chicken. But what does chicken taste like? Meat. What does meat taste like, right? So with all of these taste sensations, we cannot break it down any further, and we cannot really explain it without using the actual word. Some of them we have more sensitivity, some we have lower sensitivity and high adaptability. Would we want high adaptability for bitter? No. That means that as you eat it, you become accustomed to it and eat more of it. Now that's bad, especially if you think it's a toxin or poison. That means you're going to ingest a lot of it and you're going to die as a response. All right, now in terms of taste, taste is affected by texture and temperature. Texture affects the perception of taste. Temperature also affects taste perception. Again, cold soup, right? Some people can handle it. Anybody's ever had what we call an aspic, right? So what happens sometimes, and what we used to have, this year I think they canceled it, was our culinary program. We used to have fine dining nights, right? And they would make aspic, which is like meat that has been jellified, right? It's almost like a meat jello. Jello, instead of having, you know, strawberries, instead of having oranges in the jello, right? It's something like that, gelatinous, but with meat in it. Weird, right? So what happens is the texture is very different. It's like solidified meat with a little bit of gelatin connecting it. Most people freak out about it, right? It's usually served cold, right? And when you put it in your mouth, if you're not used to it, some people spit it out, even though it tastes pretty good. Tastes have very rapid adaptation, both at the level of the taste bud and within the central nervous system. So even the taste bud adapts rapidly. So when you take your first bite of our Leon sundae, what happens? You activate the sweet sensation really quickly. And then almost immediately, it takes even a greater amount of sweet sensation to get the same response. And since you're not adding more ice cream and more sugar into it, you don't increase the amount of sweet sensation. So the same amount of sugar no longer activates the taste buds. Taste is influenced by smell as well, giving us flavor. How many of us, when we have a stuffy nose, don't like the same stuff that we do when we're normal, right? Because it just doesn't smell the same. It doesn't then taste the same. We talked about bitter being most sensitive. Why? Because most of the things that are bitter are poisonous. In terms of taste, and we kind of mentioned it before, 3 main cranial nerves allows us to bring in taste sensation. The facial nerve, specific branch called the chorda tympani, carries sensations from the anterior 2/3 of the tongue. You don't need to know the specific one, just know it's facial, right? Then glossopharyngeal allows us to bring taste sensation in from the posterior third of the tongue. And then from the pharynx and the epiglottis, the vagus nerve allows us to bring taste sensation in from these areas as well. When you have all of them combined, then all of these facial nerve is going to have connections to the thalamus and then to the postcentral gyrus. Taste actually does end in that somatic sensory cortex. Taste goes through the thalamus. So the only thing that doesn't is smell, right? Taste, if it's on the anterior 2/3 of the tongue, for sweetness, the sweet taste buds activate. They activate branches of the facial nerve. You have an action potential now going down a branch of the facial nerve, which sends that information into the pons. In the pons, there's a synapse between secondary neurons in the pons. Then it goes to the thalamus. From the thalamus, a third neuron sends it to a specific area of your postcentral gyrus meant for sweet sensations of the tongue. And then you activate that area, and now you have that sweet sensation that's now triggered in your brain. Now you have that sensation of sweetness. Kind of crazy how intricate linked it is, right? It is one of those that, because most of our special senses do not eventually terminate at the postcentral gyrus, right? What do I mean? Smell goes to the frontal lobe. Vision goes to the occipital lobe, right? We're gonna hearing and balancing equilibrium. It's gonna go to the temporal lobe. So this is the only one that actually goes to the postcentral gyrus, and only the postcentral gyrus, right? Along with other general sensations from your body and your limbs and your face and your tongue. All general sensations end at the postcentral gyrus, but this is one of the rare special senses that end here as well. All right, I will stop right here because once we get into vision, it becomes very deep. So I will stop right here. On Monday, we're gonna go through the rest of chapter 15 and start a little bit of 16. 16 is pretty small, okay?
I have a quick question.
Hold on for 1 second.
Okay.
I'm just gonna stop recording. So then